طيب, let's continue lecture 23. Okay, let's recall example 4.5, the effective pressure drop on the conversion profile. So we said, remember, for this example, we said first calculate X, neglecting the effective pressure drop. So the resulting X was 82%. Then we said calculate X, accounting for the pressure drop. Obviously, it was much smaller. It was only 69%. Then there was a third requirement, which was finally determine how your answer to be would change if the catalyst particle diameter was doubled. So what would happen to X if I double the particle size? Of course, I'm not going to use more catalyst. It's the same amount of catalyst inside the reactor. Only I'm going to use larger particles instead of the smaller ones. Of course, we solved that as well, and the answer was 77%, right? And you already remember why we obtained higher conversion, correct? Because we said when we increase the particle size, when we double the particle size, the pores between the particles becomes larger, the resistance to flow becomes smaller, therefore the pressure drop becomes smaller, so you maintain higher pressure. Still the pressure drops compared to the entrance, but in this case, the new case where the particles are double, you maintain higher pressure because the flow experience less pressure drop. So maintaining higher pressure means that you maintain smaller volumetric flow rate. Maintaining smaller volumetric flow rate means you'll have higher concentration, which leads to higher rate of reaction, which eventually leads to larger conversion compared to the previous case where the particles were smaller. Okay, but also there were a few things that mentioned here. It said assume, so this is the continuation of part C. It said assume that the rate constant K, is unaffected by particle size. So it's an assumption, which makes you think that, so in reality, the value of K changes as the particle size changes. Yeah, true, that's true. But this time, we're assuming that the rate constant K is unaffected by the particle size. An assumption we know from chapter 12 is valid only for small particles, which means that if your particle was very small and you doubled its size, the value of K will not change. But if the particle size was of moderate size and you doubled it, the rate constant will change as well. Let's understand this statement. Okay, so again, by increasing the catalyst particle size, conversion X increased from 69% to 77%. We answer this question. We said in summary, increasing the particle size, so increasing the dP decreased the pressure drop, and thus the rate of reaction in X increased. However, chapters 10 and 12 explain that when diffusion effects are important in catalyst pellet, this increase in conversion with increasing particle size will not always be the case. See, Shabab, we just said that we doubled the particle size, we got higher conversion, right? But in cases where diffusion effects are important, this increasing conversion with the increasing particle size will not always be the case. Why? Let's see. Let's examine the catalyst particle shown below. So we have here catalyst particle. Of course, this particle is placed in a bed of particles, right? Okay, so let's see. The flow is coming and it's going around the particle, creating a boundary layer, of course, right? Okay, there's concentration gradients, and obviously the concentration of A in the bulk is more, and the bulk here is more than the concentration of A on the surface, right? Which in turn, this concentration of A on the surface is more than the actual concentration or Ca inside the particles, right? So you know that already. Right. For larger particles, you know that it takes a longer time for a given number of reactant and product molecules to diffuse in and out of the catalyst particle where they undergo reactions. Not to mention that it results in smaller concentration, of course. Okay, so we said if the particle size were much bigger than what you see here, then you have some time wasted for diffusion. So by the time or for the reactant to reach the active site, it will take it some time. And of course, the more time it takes, the slower the rate becomes. Correct? The smaller the rate becomes. Therefore, the observed rate of reaction decreases, which in turn decreases conversion. So what I see, the observed rate of reaction actually decreases as the particle size increases. This decrease in the observed or the overall rate of reaction is accounted for in the overall rate constant. So mathematically you account for it here, where Ka is inversely proportional, Kr, which is the overall rate constant, is inversely proportional to the particle size, meaning the larger the particle size, the smaller the overall rate constant, and therefore the smaller the observed or the overall rate of reaction. Right. So let's write the rate of reaction. Let's write the observed rate of reaction. Well, the observed rate of reaction equals the observed or the overall rate constant times the concentration of A in the bulk. So the overall rate of reaction equals the overall rate constant times the measurable concentration of A, which is in the bulk. Okay, where Kr is the overall rate constant and Ra is the observed or the overall rate of reaction. Type. What happens if the flow goes faster? So here you have low velocity. Now the velocity is higher. The flow velocity is higher. What do you notice? Well, you notice that the boundary layer becomes smaller, right? What happens if the velocity was increased beyond this value? Obviously, the higher the velocity, the smaller the boundary layer until it vanishes, until the concentration of A in the bulk becomes similar to the concentration of A on the surface, because we don't have a boundary layer anymore. We do not have a boundary layer anymore. So in the absence of external diffusion, I don't have external diffusion because I do not have boundary layer, right? So the absence of external diffusion limitation, CAS, the concentration of A on the surface of the particle, equals the concentration of A in the bulk. Therefore, the above equation can be written as 1 Ra equals Kr times CAS. Ca, concentration of A on the surface, which is the same as concentration of A in the bulk. طيب. So again, Kr is the overall rate constant and minus Ra is the observed rate of reaction, and we say it in the absence of external diffusion, Ca at the bulk equals Ca on the surface of the pellet. Therefore, we can write the rate law this way. Right. Now we are plotting Kr versus dP. Remember, we said the overall rate constant is inversely proportional to dP. So this is how it looks like. Let's see. Imagine I have a particle size that is this big. Tamam? And obviously the particle size is very big. and therefore there is huge internal resistance to mass transfer, right? Okay, so we have all of these channels which are very long, and they are tortuous because these channels are not straight. They're going up and down, left and right. They narrow down and then they widen up. All of this creates resistance toward the internal mass transfer, the internal diffusion. Therefore, you have the rate of diffusion very slow, and the overall rate of reaction becomes very small, and it shows up in the value of Kr. You have a smaller Kr, right? Larger particle size, you have a small Kr. So if I decrease the particle size, Kr, the overall rate constant, increases, right? It increases. And actually, when I'm here, we have the internal diffusion is the slowest step. Why you have a small overall rate of reaction? Because the internal diffusion is limiting the overall rate of reaction. Tamam. However, if I decrease the particle size to a very small size, now if I cut it into half, okay, so take this dp and cut it into half, does the Kr change? No, it does not, because the Kr has reached its maximum value. So at small particle diameters, Kr is large, right? Small particle diameters, Kr is large, right? It's large. And you can see, Shabab, even if I double the particle size, so imagine this is my particle size, I double it, right? Kr remains the same, right? The overall rate constant remains the same. And that was the assumption we explained. Anyway, so again, at small particles diameter, Kr is large. Actually, this Kr, the overall rate constant, is almost equal to the kinetic R, right? So I don't have any other resistances. Remember these 7 resistances with the seven steps involved in the catalytic reaction, where each step has its own resistance, right? Or it has its own 1 over K conductance, right? Imagine now I don't have the external diffusion both sides for the reactant, for the product. So we have 5 steps, correct? And the particle size is so small that even the internal diffusion is not an issue, correct? So what's really limiting the reaction is the surface reaction sequence, right? So here Kr is at its maximum value. It's almost equal to the kinetic K, right? So it's not, there's no mass transport limitation involved in this Kr. Right. So Kr is large and at its maximum value, right? So you have Kr is large, so you think the rate of reaction should be large. However, if you have very small particle size, that means the voids between the particles would be very small. So the resistance to the flow will be high. The flow will experience high pressure drop. The pressure will reduce. And the volumetric flow rate will increase, will be large. Therefore, the concentration will be small. The rate of reaction will be small. Right? The rate of reaction will be small, and you will end up with a small conversion. So at a small particle size, at a small particle diameter, Kr is large and at its maximum value, but delta pressure, delta P, the pressure drop, is also large, resulting in a low rate of reaction and conversion. So here we go. Very small particle size, very large pressure drop, resulting into small conversion. So here actually you can see, even if I increase the if I increase the particle size, here the conversion increases because the pressure drop reduces. So here we have the pressure drop is dominating. So what's limiting the conversion? It's the pressure drop which is limiting the conversion. Okay, and as I increase the particle size, actually what I'm doing is I'm reducing the pressure drop, which increases the rate of reaction, which increases conversion. At large particle diameters, the pressure drop is small, but so is the overall rate constant Kr. The overall rate constant Kr is small. Why is that? Because you have lots of resistance in the for the internal diffusion. So actually the internal diffusion is the slowest step because the particle size is large, right? So that leads to small overall rate constant, and therefore the rate of reaction is small, resulting in a low conversion. So here we go. At very large particle size, again x is small because kr is small. If I decrease the particle size, I enhance the internal mass transfer, so I reduce its resistance, so the overall rate constant increases, leads to a higher rate of reaction and therefore higher conversion. Okay, so thus we see a low conversion at both large and small particle diameters with an optimum in between. So very large particle size is bad because it will lead to a small rate of reaction due to the high internal resistance to diffusion, right? And very small particle size is also bad because it leads to high pressure drop, leading to small rate of reaction, leading to small conversion. Okay, but of course the reason for getting small conversion is different, because at high particle size we have the internal diffusion inside catalyst dominates, but at small particle size the pressure drop dominates. And then obviously we have an optimum value for the particle size where the conversion is at its maximum value. Okay, so with this we finished talking about the diffusion. Now we have one more topic and we call it a day. Right, so we understood that pressure drop does not do you much good, right? Because it reduces your rate of reaction. So would you do anything just to reduce pressure drop? Would you always want to minimize pressure drop, or some pressure drop is useful? If pressure drop is to be minimized, why not pack the catalyst into a larger diameter tube to decrease the mass flux, thereby reducing the pressure drop? Correct? So basically we are saying, instead of having a pipe that looks like this with a 1 liter volume, you say, we'll have a pipe which is larger, still 1 liter volume, but larger. Because if you use larger diameter tubes, obviously you reduce the mass flux, correct? Remember the mass flux? So the mass we already divided by the cross-section area. So if this is large, the mass flux is small, right? Remember the mass flux equals rho times the velocity. So if this is small, right, you have small velocity. That means small, if you have small velocity of the flow, you have a small resistance to flow, therefore smaller pressure drop, correct? Okay, so why don't we do this? Okay, remember, let me show you again the effect of G. Okay, so if you have here small g, because the diameter of the tube is large, so G is small. If G is small, beta naught is small. If beta naught is small, alpha is small. Remember, we said smaller alpha represents smaller pressure drop, right? Okay, yes. So does that mean we want to eliminate pressure drop? Actually, you don't want to eliminate pressure drop. Some pressure drop is important. There are two reasons for not increasing the tube diameter. So we said we will not do this. We will not actually use larger diameter tube just to eliminate the pressure drop. We'll not do that. There are actually two reasons for not increasing the tube diameter. What are these two reasons? Well, there is an increased chance the gas could channel and bypass most of the catalyst, resulting in little x. Because if I increase the diameter, then the length will be shorter, correct? And if you have a small portion of it is not well packed, this small portion could be, for example, 20% of the tube. But if you have a longer tube, because it's a smaller diameter tube, so longer, of course we are keeping the volume the same, then if a small portion of the tube it's not well packed, that might be only 10% or 5% of the tube. So that's why I don't want always to choose a higher diameter or tube with bigger diameter, because that might lead to bigger chances for bypassing due to bad packing. That's one reason. What's the other reason? The ratio of the heat transfer surface area to the reactor volume, catalyst weight, will be decreased. Again, if I have small diameter tube and I use, instead of the small, I use a larger tube, what am I reducing? I'm reducing the surface area, right? The surface area of the tube. And you know that the surface area is where heat is transferred, right? So in this case, at the small diameter, you have more surface area, right? More surface area per volume compared to this setup. You have less surface area. So if I increase the tube diameter, so the surface area will decrease. If I decrease the surface area, I will not be able to remove heat at enough rate, or add heat at enough rate. So again, the ratio of heat transfer surface area to reactor volume will be decreased if I increase the diameter of the tube, thereby making heat transfer more difficult for highly exothermic and endothermic reaction. So for these two reasons, actually I do not choose pipes which are very large in diameter, just so that I decrease the pressure drop. That is really not a wise decision to do. Okay, with this we reach the end of today's lecture, and we'll meet inshallah soon.